Okay, lesson 121 is about graphing piecewise functions, and this should be a fairly short lesson because this is pretty straightforward. So let's just look at some examples. So example 121.1, we want to write the equation for this function. Now if you look at this function, it looks kind of strange. It's not very smooth. It looks like it's made up of a bunch of little pieces and parts, and that's exactly right. So if you look at like the area in here, this seems to be one kind of graph or one kind of function, and then we jump to this next spot here. This seems to be sort of a completely different kind of graph, and then we have, you know, a third different one as well. So it seems to be in these three pieces. And this is why it's called a piecewise function, because there are different areas of our different pieces that have different behaviors or come from different functions. Okay, and that's very easy to take care of. We just define it a piece at a time. So if we were to write the equation for this function, we'd say, well, f of x equals, and then we break down the domain into pieces. Well, here, okay, we've got just this horizontal line between an x value of 0 and an x value of 1. So if x is between 0 and 1, it's defined one way. And exactly what is it? Well, it's just the function f of x equals -1. Just that horizontal line. Okay, so that's that first piece. And now the behavior changes between 1 and 3. So if x is between 1 and 3, we have a different kind of behavior. And so in fact, if we look at this, the slope of the line is going to be rise 1, run 1, rise 1, run 1. So we have, you know, just a 1 times x, and think about where that y-intercept would be if we continued that down. It would be at -2, so that line would be x minus 2, so a slope of 1 and a y-intercept of -2. Now we're not, you know, we obviously never get the -2. When we put a 1 in there, 1 minus 2 is -1, and that's where it's at. And when we get up to 3, 3 minus 2 is 1, and that's where it's at. Okay, so we only have a portion of it because the domain is restricted to 1 to 3. And the last portion is in this green box, and this is if our x values are bigger than or equal to 3. So if we have, here's 1, 2, 3, so anything bigger than 3 for any of these x values, we just get a +1. And we just sort of put all those together, and now we've defined our function as a piecewise function, where we've just looked at the different pieces of the domain, and for each piece we've written the function that describes the behavior of the function and in that portion of the domain. Okay, so let's do another one. We want to write the equation for this function. Well, this one's even maybe easier. It's got two pieces. Okay, so we've got, I'll just go ahead and box them. So we've got, you know, this portion here, and we've got this portion here. So we've just got two pieces. All right. So let's look at this one, and this in particular is if our x values here are strictly less than 0. So anything going this way. And notice we've got this sort of this hole here, so it's not this green portion is not defined on x equals 0. It's just right up to x being 0. So make sure you don't put an equal in there. Okay, and what is it going to be if x is less than 0? Well, this is 6, 7, 8, so it will just be 8 for our first piece. And then if x is bigger than or equal to 0, So, oh, I said 0, not 1, 0. So here at x being 0, and also for any other x values that are bigger than 0, we will get a line that has, let's see, it will rise 1, 2, 3, 4, 5, 6, and run 5. So 6/5 is the slope. So that's 6/5 x. The y-intercept is 0, so it's like plus 0. We don't need to write that on there. Okay. And then maybe a note to make here, and your book didn't really use this notation, but you'll probably see this at some point, so we maybe should just mention it here. Sometimes they'll just put, this kind of notation if x is less than 1. Another notation that you can use, though, is what we call interval notation, and you'll use this probably in pre-calculus if I recall correctly, but definitely in calculus. So here, if the x values that we would be considering is anything from -infinity up to 0. Now, if you put a angular bracket around these two endpoints, that would mean it's included, like an equal sign. This is not included, so I would just put this kind of curved parentheses on this interval. Okay. And then for this one being greater than or equal to 0, the left bound would be 0, and it includes 0, so I would put a square bracket there, and it goes for infinity, and you always put a curved parenthesis by an infinity or a negative infinity, because it's not really a number, and you can't include that. You can't be like equal to infinity. That doesn't even make any sense. So you always put a curved parenthesis by an any magnitude of infinity. Okay. All right. Oops. We already did that one. I'm going the wrong direction. Okay. So before we do this one, I'm just going to show you how to write out these interval notation, just so you get used to that. So here you would say -infinity up through 0. 0 is included here, so I'd put a square bracket, and because we have some kind of infinity, there's always a parenthesis, a curved bracket there. Okay, here we put 0 to 2, and there's no equal signs there, so we would just put the left bound of 0 up to 2 and put curved brackets or parentheses around those. And then here, 2 is included in our lower bound, and it goes up to infinity. Okay, so that might be another way that you would see those intervals written. This is called interval notation. And this is a little bit more convenient. Notice it's a little bit easier to write than having to put all these less than and greater thans. You can clearly see that this is the left side, the lower bound, and this is the right side, the upper bound. So this is nice notation. Okay, so let's go ahead and graph this. Okay, so from -infinity off this way forever, up until we reach 0 right here, we're going to have a line that looks like 3 plus x, or you can think of that as x plus 3. So imagine x plus 3, that would, here's 1, 2, 3, it would cross the y-axis at 3, and then it would have a slope of 1. So it would go this direction like that. Okay. Then between 0 and 2, so here is 2 and 0. Okay. Then we would have x. Okay, so in this particular instance, it's not defined here. Okay, and then it would oh, sorry, I did the wrong size. Like, this doesn't make sense. This is wrong. I did it. We were supposed to go -infinity to 0, so that we should have the other part of the line here. I just noticed that. Sorry about that. Okay, so pretend I didn't put that there. It's like, wait a minute, this isn't going to be a function. Okay, so we have this line. We need to make sure that we went from negative infinity up to 0. Okay, and then from 0 to 2, we're just going to have the line with slope 1. So imagine it's got that point and that point on it, and now it's open at 2 as well, so we need to put a circle there. Okay, so it doesn't actually include that point, and it doesn't actually include that point. It's just everything between those. And then from 2 beyond, okay, we have the line that looks like 3 minus x. So again, it would be the line that kind of intersects the y-axis up here at 3, but then it has a slope of -1. So it would rise -1, run 1, rise -1, run 1, rise -1, run 1. Okay, so it would cross here. And imagine what that, would look like. This direction. Okay, so if we put 2 in there, that would be at 3 minus 2 is 1. I guess I drew this a little bit too tall. So at 2, 1 is where it would start. Okay. Okay, so again, we've got this piecewise function. We've got 1, 2, 3 different pieces. Okay. And the last thing to discuss, they talk about the greatest integer function, and closely related to that is the least integer function, so I want to talk about that as well. So the greatest integer function, and the notation they use for it is f of x equals, and then you put these little square brackets around it. I find that that's probably not the most common notation. I think often you would see it written like this. Oh, actually this one is written like that. This one would be actually written like this. This can be confusing. Okay, so the greatest integer function, this stands for the greatest integer that is less than x. Less than or equal to, actually. Okay, so what this means right here, these are both notations for the same thing. This is the greatest integer that is less than or equal to x. So let's do a few examples. So for example, like f of 1.7. So what is the biggest integer that you can think of that's less than or equal to 1.7? So there's lots of integers less than or equal to 1.7, like -13 is less than 1.7, but 0 is also less than 1.7, and 1 is less than 1.7. But 1 is the greatest integer that's going to be less than or equal to 1.7. So in this case, it will be 1. You can almost think of this as kind of like a round down, but it's not rounding, because rounding, of halfway, that kind of thing, it's just go down. Okay, and that's why this is a very nice notation, and we call this the floor function. So think about 1.7, okay, is in between the 1 and 2. Okay, on the floor is 1, and on the ceiling is 2, and 1.7 is somewhere in the middle. So we're going to go to the floor. Okay, so hopefully you can imagine what the least integer function would be. Well, this is the least integer that is greater than or equal to x. So if we did f of 1.7 here, and took the ceiling of 1.7, well, again, the floor on the floor is 1 and on the ceiling is 2, because 1.7 is between 1 and 2. So the ceiling function, okay, that would return a 2. So this goes up to the next integer and this one goes down to the next integer. Okay, and then if we were to look at the graph of this, okay, think about, let's just start at 0 for instance. Okay, well the floor of 0 is just 0. Okay, but let's say we had 0.1. Well, that would also go to 0. And 0.2 and 0.3, all those things would go down to the floor of 0. But when we get to 1, okay, it's going to hop up here. The floor of 1 is 1. Okay, so this would keep going down to 0 until we got to 1. But then 1.1 and 1.2 and 1.3 and 1 all the way up to, you know, anything, 1 point anything, if we go to the floor, it would be 1. So it keeps going, looking like 1, right until we get to 2. But once we get to 2.0, well, that's going to go up to 2. And so you can imagine we are going to get this kind of behavior. And it's going to go. Okay, and often we call this a step function, because it just looks like you can have these little steps that you can climb up. Now this is also a step function. It looks very similar. Okay, but this time we're rounding up. So 0, I mean, it's already at 0. But if we have anything bigger, 0 point anything, we're going to go up to the ceiling. Well, 0 point anything, the floor would be 0, but 1 would be the ceiling. So as soon as we get beyond 0, it's going to hop up to 1. Okay, so it won't be there, but it will be at 1 all the way up until we get to 1. When we get to 1.0, okay, its ceiling is still 1, but anything over 1 is going to hop up to 2 because we're going to go to its ceiling. Okay, so it looks fairly similar, but you can see sort of the open holes are on different sides, and sort of the steps are up one from these ones. Okay, so these least integer and greatest integer functions, or the floor, and this is the ceiling function, okay, are these step functions. And again, they look like they're broken into pieces, but we don't write them in intervals like, oh, if it's between 0 and 1, it's this. Between 1 and 2, it's this. Between 2 and 3, we would have to do that an infinite number of intervals, and we don't have enough time to write an infinite number of things. So there's a better way to write these kind of piecewise step functions with just one convenient notation.